Alrighty, welcome back to operating systems. So this is the second hump in the course. So we are beginning our journey on threads. So hopefully with all our practice with processes, starting threads won't be too bad, but it'll get hard again, and then we'll be over the hump, and then the rest of the course will be not as bad as this. So let's dive into threads, but before that, we have to talk about concurrency and parallelism and what the difference is between them. So I kind of alluded to it in like the first lecture that they aren't the same thing to us because reasons, and the reasons will become apparent soon. That's annoying. All right, so they are not the same things. So to illustrate that, so concurrency, when we talk about software, is talking about switching between two or more things, which means you can get interrupted. You can stop progress on one thing and switch to something else. And the goal for concurrency is to make progress at multiple things, and you can switch between them. Parallelism, on the other hand, is running two or more things at the exact same time. So at the same time instant, two things are running. And in this case, they would be independent. That goal is to run as fast as possible, do as many things as you can at once. So here's some real life situations so we can figure out what we can do in parallel and what we can do concurrently. So assume you are sitting at a dinner table and you are not a savage and you are a polite human being. So at this dinner table, you can eat, drink, talk, and gesture with your hands. Say just one hand is fine. But we have a weird caveat here where you're so hungry that if you start eating, you won't stop until you finish. So given that, what tasks can be done concurrently and what tasks can be done in parallel? So pick any two and say whether or not we can do them in parallel or concurrently. Yeah? Yeah, so talking and gesturing I can do in parallel. I could also do it concurrently because I could do them both at the same time, and I could just switch between them at any given time. Between gesturing and eating, well, I have to eat with my mouth, and if I start eating, I won't stop. So I can't do them concurrently because I can't switch from eating. But I could do them in parallel because I could just use my one hand while I'm shoveling food with the other. Maybe we're somewhat of a savage. And then, let's see, between drink and talk, can we do those in parallel? Drink and talk. No, right? Yeah, so I can't drink and talk in parallel, assuming we are not savages. Some of you might be able to like, but that's like, doesn't count. So I can't drink and talk in parallel, but I could do it concurrently. I could stop drinking and talk, and then I could resume talking, resume drinking, switch back and forth between them. So I could do those not in parallel, but I could do them concurrently. And I think that's pretty much anything. So any questions about the difference between parallelism and concurrency, or does that make sense?
So anything that can be done in parallel can be done concurrently, right?
Yeah, pretty much anything you can do. Well, in this case, sorry, what did you say? Anything you can do in
parallel can be done concurrently?
No. So in this case, I can't because of that weird condition where I'm so hungry I can't stop. Well, I could do eat and gesture in parallel. So I could, shovel and gesture with my hand, but I couldn't switch from eating because apparently I'm too hungry. I couldn't do it concurrently because I can't stop eating.
That's literally only because of that one thing.
Yeah, that's literally just because of that condition. And in general, for computing, if you can do something in parallel, you can do it concurrently.
So in general, it is the case.
Yeah. In general, it's the case. This is just like a very contrived example to get that case, just to say that it's not always implied, but in software, it's pretty much always implied. All right, good. All right, so here's all the things if you need to review them or if you're watching the slides or whatever. So like drinking and talking, I can't do them in parallel and I can't do them concurrently because of that condition for eating. basically I can't do anything concurrently with eating because of that condition. And my limiting resources, I have like my hands and then my mouth. So I can't talk and drink at the same time or eat at the same time. They all conflict with my mouth resource, I guess, so I can't do anything in parallel with that. But I could do something with different resources like my hand and my mouth. So that's good. Any questions about that? So this will become more important as we go on with this. So now we have to talk about threads. So luckily or unluckily, they are pretty much exactly like processes, except that they by default share all memory. So there's the same principle applies. Each thread has their own virtual registers. So that would include the program counter, its current stack, and they also get their own unique stacks as part of setting up a thread. But they're in the same address space. So if you modify a global variable, it's modified in all threads, which will be the bane of your existence going forward. But we'll just go ahead and ignore that for now, and that will be the tricky subject we get into later. So in here, if you want to have memory independent to a single thread, you have to ask for it explicitly for something called TLS, or thread local storage. So by default, the stacks will be local to a thread, so they'll be in thread local storage. And later, if you want any information, any other information only local to a thread or independent between threads, it has to be in thread local storage. So we won't really use that, but by default, your stack will be independent for each thread. The fun thing about this is processes can have multiple threads. So a thread actually lives within a process. So by default, a process just executes code in its own address space. But once you have threads, there are multiple, I guess, virtual registers going around, and multiple executions can take place in the same address space. So because of this, whenever we create a new thread, we're just creating like a new virtual CPU. You can think of it that way. We're not creating a whole new process. No, we're not creating new virtual memory. We're not creating new file descriptors. We're not copying page tables. We're not doing anything like that. So creating threads are way faster because we don't have to do any of the other information. Like, it's only virtual registers, not creating a new copy of all other information that are within a process. So because of that, they by default share data, but they're also way less expensive to create and less expensive in terms of operating system memory, in terms of CPU time, are the main things. So assuming you have one CPU, threads can express something like concurrency. So a process can like appear like it's executing in multiple locations at once, but it's not really. The OS is just context switching between processes really, really fast. Might be able to execute concurrently. So what we could do is every time we have a new web request here, so like if you were at the sockets example, every time we have a new connection, we can create a new thread that handles that connection, and then the kernel can go ahead and schedule the threads to run in parallel or concurrently, and it looks like lots of things are happening at once. So even with a single CPU, all your threads running concurrently can look like they're running in parallel, just like when we had multiple processes and we switched between them really, really fast, it looked like all the processes were running at the same time. So they are lighter weight than processes. So in processes, right, each process has independent code, data heap because of virtual memory. But in a thread, everything is shared between all of the threads. So they live within a process. So they share code, they share data, and they share the heap. So there might be some conflicts if you're trying to modify memory in multiple threads. A process was kind of nice because it had independent execution. So one process did not affect another process at all. But because threads live within the executing process, they affect one another. So even if a thread modifies the file descriptors. Well, suddenly in every other thread, it's modified because when you modify file descriptors, it's only tracked by the process. And all the threads live within the process, so any change you make affects all threads. So the only part that is the same is in a process, it has its own stack and registers. That's all independent. And threads also have their own stacks and registers. And that's the only part that is independent within threads. So processes are really expensive to create and to do the context switching for, because they have to copy all virtual memory, right? We have to set up page tables. It would have to copy all the file descriptors, set up new page tables, new virtual addresses, all of that stuff. With threads, it's really cheap to create them. We just create new virtual registers and set aside a stack. And context switching is also pretty quick, because if we context switch between threads in the same process, well, guess what? They're using the same page tables. We don't have to flush the TLB. We don't have to do any of that. All the entries are still valid, and it's just much quicker to do. We don't have to switch anything else. When a process exits, it gets completely removed from the operating system whenever it exits or terminates, assuming someone calls wait on it and is a good parent. But with a thread, whenever a thread exits successfully, all that happens is its unique stack gets removed, and that's it. And the fun thing here is when a process dies, all threads within it die as well. Yeah.
Sorry, so the meaning of using threads, like I can see why it might be useful when you parallelize those threads, but if it just context switched, then what's the useful of it?
So if it context switches, the context switching is still pretty quick, and maybe you want to switch between tasks a lot to like make it appear that they're running in parallel. And sometimes it's just easier to program that way. So if I want to, it'll be the only way that I could accept multiple connections or something like that, or work on multiple files at the same time. I could just have threads switch between them while it's doing something. So yeah, you will find threads very useful, and we'll see some thread examples too. So for this, we'll be using POSIX threads. So Windows, there's a Win32 thread, but we're going to use Unix threads. So this works if you're on Mac OS, and if you're on Windows, well, you're not really developing anything terribly worthwhile. Okay, that's probably a bit of an overstatement, but most server stuff and most heavy-duty software, it's all running Unix anyways, so we do pthreads. Principles still apply, just the APIs will be different. So to use pthreads, you just include the pthread header, and whenever you compile, you just add on the -pthread flag to both the compiling and linking steps, and it goes ahead and adds it for you. For anything you use, the build files will already do that for you. So all the pthread functions have documentation. You could look it up in the man pages or on the internet or whatever. So the API for that, we'll get into some examples. So to create a thread, to create a process, we use fork. To create a thread, we use something aptly named pthread create. So it takes 4 arguments, and the first one is the pointer to a thread. This is a structure that you don't know the contents of, but you just give it a pointer, and you have this function initialize that structure for you. So the attribute, the second argument here, is just some thread attributes. For now, you can just give it null and not set any attributes and accept the defaults. We'll see some more details how to change this later, but for the most part, you can just accept the defaults, and we will figure out what the defaults actually do. The next argument is a start routine, which looks like an ugly C type, but if you read that, all it wants is a function which takes a single argument, takes a single pointer argument. So in C, a void star essentially just means a way to tell C it's a pointer to what? I don't know. It's just a pointer. I don't care. So this is a function called start routine that takes a single argument, which is a pointer, and returns a pointer. So all those stars shouldn't look that scary. It just needs a function to run whenever the thread starts. And then the last argument here is a void star arg, and that will be the value that is actually passed to that start routine function whenever it runs. So this function returns 0 if it's successful, and unlike the system call wrappers that return -1 and then set error no, this one just returns an error number directly. So just check if this returns 0. If it doesn't return 0, it gives you the error number. And if it gives you an error, the contents of the thread are completely undefined. Yep.
The parameter void start routine, does start routine have to return void?
Start routine returns a pointer, so a void star.
Okay.
Yeah, so you like read it inside out kind of, so this is just a pointer to just a name start routine, and because it's in brackets, it means it's a function, and this just is the arguments, so just a single pointer, and then returns a single pointer. All right, so that's how to create threads. So let us get into an example and also see why they are heavier weight. So go to code. So here's, no, I don't want that one. Oh, wait. Create for. Yeah, I want create for. All right. So here is our testing whenever we're creating new processes. So we create a new process by calling fork. So here I define a variable called, or define something called endforks. That is 50,000. And what I will do in this function is, well, I will loop 50,000 times, fork, and then check if there's an error. If I am the child process, I just immediately exit. And otherwise, in the parent, I'll make sure to wait for the child to make sure I clean it up so I don't create a zombie process. And then I just go through this loop again. So every time through this loop, I make a single child and I wait for it. So this will create 50,000 processes, correct? All right, so since this creates 50,000 processes, I can see how long it takes to, to create 50,000 processes. So 6.9 seconds, nice. So let's see what the thread version of that looks like. So in the thread version, here I create some attributes that we can ignore for now, but it's the same variable. So n threads is 50,000. So this loop executes 50,000 times. It creates this pthread variable, and then it calls pthread create, gives it the address of that thread, the attributes, which we could have just set it to null, and then the function to run, which I just called run. And then it gives it, you can set the argument. I'm not going to use it, so I'm just going to set it as null. So in here, this will create a thread, and that thread will go ahead, start executing this function, which just returns 0 or just returns null. Same thing, it just doesn't do anything. And then there is an equivalent of wait, which we'll get into later, but you can just trust me that I did that. So for that, I'm creating 50,000 threads, and if I time that and check, it is 4 seconds, which is a bit faster, which should be a lot faster. All right, whatever. It's still much faster. It's still like almost 2 times as fast. It should have been like a second, but I guess my computer's struggling for some reason. So, yeah, and here's another example of just how to create threads. So it's a bit different than processes, but hopefully it makes a bit more sense. So this is like the minimal amount of code you need. Just create a main, create a thread on your stack, then you initialize it through pthread create, give it the attributes, so by default you can say null, then give it which function to run, and then what argument to pass it. So in this case, after I create the new thread, it would start run, and then my original thread that was running main would just want to execute this line next. So this is like the same situation whenever we made processes where we don't know which one is going to execute next. So yeah, so it's a bit different. So then processes, do we like this better than fork, or is specifying a function to run make more sense? Yeah.
I think it kind of makes more sense, especially if you want to do something else with it, like you have multiple runs that do different things.
Yeah.
Parallel.
Okay. Yeah, it usually makes more sense to me, and it's clear to read because I know exactly what the other thread is going to start executing. With fork, you just have to argue at the time of the fork, hey, it splits off, and then two of them can continue at the exact same point. Although before, some other people preferred fork for some reason. Not quite sure about that. So are there some differences, or are we missing anything that we would have if we were doing this using a process instead? The weight. Yes, I was not a bad parent. Or sorry, I am a bad parent. So that's the main thing we were missing, and there is a weight equivalent for threads. Annoyingly, it is not called pthread wait, it is called pthread join. So how it works is it takes a thread to wait for, if we were doing processes, or a thread to join as an argument, and then it takes this ugly thing, which is a pointer to a pointer for the return val. All this is going to do is write a value to that address you give it, and that's the way to get a return value out of a process, or read whatever it returned from its start routine. So you can think of this as the same thing that's happening whenever you call wait and you give it the address of the W status. This is the same thing. You would create a pointer and then give this the address, and then it would write the value of the pointer there. So same thing happens. Threads luckily have a pretty much exact equivalent with processes. So for this, it returns 0 on success, error number anyways, and just like processes, you can only call this one time, like each thread, you can only call this on each thread exactly once. Multiple calls on the same thread leads to complete undefined behavior because, well, with threads, they're all in the same virtual memory space. The kernel's not super managing them, so it's hard to tell if it's already dead or not. So, like if you call wait on the same process multiple times, well, you can't because the kernel just cleans up that process and deletes it. You just get an error directly. With threads, it's a bit more difficult. You just get undefined behavior, and you're left to your own devices for that. So here is that same example fixed. So in it, I would just call pthread join, and now the resources are cleaned up. So if I go ahead and let's make that change.
So that means if you create a thread, you can like, I don't know if you wanted to wait specifically on that thread. Like you can, like now you can kind of choose.
Yeah, so you wait on a specific thread, but we could do that with processes, right? With wait PID. So you're forced to wait on a specific thread. There's no like join on any thread here. So it's like you only have wait PID with a specific process or thread, yeah.
I'm sorry, so for this example, do we also not know exactly what will happen first in main or in run?
Yeah, for this example, you wouldn't know what would happen first in main or run. If I execute it, well, in fact, because I didn't join here, I don't even see in run. So this time when I executed it, well, I created it, this printed, and before this thread actually ran, return 0 from main is the same as exit, so it would have exited the process, everything's gone now. So if I do this, pthread join, I have to give it the thread, and then I don't care about the return value. So here is the example where I join it properly, and I should see both messages all the time because I'm actually waiting for the other thread to finish executing. Yep.
feature join
Y-
just with execute.
So if you just did like this,
And remove the line 14.
let's see if it will implicit me. Good enough. Yeah. So
So what's it up? Why do we necessarily have to call feature join then?
So you're not guaranteed, like this is only happening because my computer is really fast. Most computers are really fast. A second is an eternity. So they'll both print by them, but you're not guaranteed. So for all of this, you want to be guaranteed something will happen, then you know it will execute perfectly. Because if you just slept and your computer, it worked for you, and then you gave it to someone else, and they're like, it doesn't work for me, because they're like executing it on some toaster or something like that, guess whose problem it is to fix it? Yours. And you will spend like 2 years of your life debugging that. All right, so yeah, in this case, I see every time I execute it, oh, there, I got them in a different order. Woo! So you're not guaranteed you always get them in the same order, but you're guaranteed you always get both messages in this case. So after pthread create, I have 2 threads. You can think of it like 2 processes. You don't know which one is going to start executing next. And it just so happened that this thread executed first in one case, and then the thread that was executing main executed. But normally you'll see in main in run. But as you can see, you can't depend on it. And we'll see how to make this dependable, and that's like the hard part of the course. Yeah.
So because all threads die when the processes die, there's no concept of like zombie threads or orphan threads.
So the question is, so if all threads die when a process dies, is there no concept of orphan or zombie threads? So would zombie threads still be a thing? Anyone want to think about that a little bit? So could a thread finish executing and I essentially don't wait for it? Because that was the condition a zombie happened. Yep. So whenever the function is done, it means the thread is finished, but we haven't waited on it yet. Or in this case, joined it. So if we did that for a process, what's that? Yeah.
In your earlier slide, it says when a process dies, all threads die within it too. So.
Yeah, but in this case, that thread could finish and the process is still alive. So if the overall process is still alive and this thread finishes, then if we don't wait on that, if that was a process, would it be a zombie process? No, it would be, right? So if you create a child, the child terminates, and you don't wait on it, it's a zombie, right? So if it was a process, so that would be a zombie process, right? So same thing, just substitute the word process for thread, and then wait for join. So if I have the case where I create a new thread, and it finishes, so it finishes running its function, that means it terminates, and I don't join it, that means I would have a zombie thread. So for instance, like it wouldn't waste that much space, but each thread has its own stack, and I have to join it so it can delete its stack and all that fun stuff. And you will also figure this out because you will be implementing threads in Lab 4. So if it's not clear, it will be. So yeah, you can create zombie threads, but we cannot create orphan threads because as soon as, and that's why, because as soon as the process is done, they all get deleted. So they don't get reparented or anything because they just now don't exist. So there is a concept of zombie threads. There is no concept of orphan threads.
So the kernel handles, like, is it like a subrepo for zombie threads as well?
No, so just, there's no subrepo for zombie threads. You just have to, you're the only one responsible for it, so you have to join it. So just like if your process keeps on running while you have children that are zombies, the kernel's not going to do anything for you, right? you'll just hold on to the zombie as long as you exist, and then they'll only get cleaned up once they get reparented. But in this case, there'll be zombies for as long as this process exists. If this process no longer exists, everything just gets deleted. Yeah.
So just to reiterate, so the pthread join also like does all the cleanup, right, and deletes everything after.
Yeah, pthread join will do all the cleanup for that one thread that is now gone or terminated. Yeah.
So is there like a way to know that you didn't properly clean up a thread, like would Valgrind complain or I don't know, something to know?
Valgrind would not complain. You might be able to, typically there's nothing that will do that because it's hard to know your intention if you just wanted it to kind of die. We'll see how to actually have automatic cleanup. That is something we can do, which is different than processes. So yeah, let's get into that because that's a perfect segue. But before that, let's go with the other equivalent. So in processes, you can terminate a process by calling exit. Unsurprisingly, you can terminate a thread by calling pthread exit. Thankfully, this one's named something we actually want. So all it takes is a return value. So by default, main returns an int. For threads, by default, they just return a pointer. So this is like the exact same as exit with an int, but because it is a thread, it is exit with a pointer. So that is the return value that's passed to something that calls pthread join on it in order to capture its return value. So also note here, if your start routine finishes or if you return from your start routine, that's the exact same thing as calling pthread exit. Just like if you return from main, that's the exact same thing as calling exit. For a thread, the equivalent is if I return from my start routine, that will automatically do pthread exit, and it's implicitly called for you. So now we can talk about detached threads. So this is where we deviate from a process. So by default, threads are joinable, which means you have to wait on them. We have to be good. Well, I guess we're not parents in this case, but we have to wait on them. We have to be responsible people. I don't know a good word for it. And then they can release their resources. So if you don't care about the return value of threads, and sometimes you will not, well, you can just save some time. You can create a detached thread, and that will make the thread automatically release its resources whenever it terminates. The only drawback here is you cannot get its return value back. But if you don't care about it anyways, then just make a detached thread. You don't have to wait for it. And it just cleans up whenever it's finished. You will not create zombie threads in this case. So you can call pthread detach on a thread, and it will make the thread detached. Again, it would return 0 on success, error number otherwise, and if you call detached on an already detached thread, so if you call detached twice, that's undefined behavior. Again, C can just go ahead and delete all your files on your machine. So in this case, a detached thread are not join. So if I run this code, so let's see this example. Touch error. So if I run this, all I see is in main. Why is that the case? Yeah.
Maybe because the main finish are too early, so it kills the threads before it gets to run.
Yeah, so in this case, what would happen is whatever thread starts executing main, generally you just call it the main thread. So the main thread comes in, creates a new thread structure, creates a new thread that wants to run with no arguments, and then it detaches it. So now we cannot join it, and we don't know which one will execute next. Most of the time, the main thread will go ahead, print in main, and then return 0, which is like calling exit. So that terminates the process, and now all the threads are done. The one that was about to run or to print in run just never executes. So before, all I could do was just, to fix it, I did a join here, right? But now it's detached. So what can I do to make sure it always prints? So what I can do is, instead of calling or saying return 0, which is the same as calling exit, in the main thread, what I should do is actually call pthread exit. So in this case, if I run it, well, the nice thing about pthreads is, by default, it will not terminate your process using pthread exit unless it is the last thread running. So if the last thread running calls pthread exit and there's no longer any threads running, well, nothing can execute, so your process just gets ended nicely. So if we compile this now and run it, we see both messages, because even if the main thread runs first, it calls pthread exit instead of exit, so the process still exists, and there is a thread that wants to execute run, so it would printf in run and then return null, which is the same thing as pthread exit. Since it's the last thread, when it calls pthread exit, the library is smart enough to realize that, oh, nothing else can execute, so I may as well end the process. So in this case, pthread exit is not kind of like wait. Wait, what's koa wait? So yeah, pthread exit is more just like, it's a bit different concept for threads as opposed to processes, because if we terminate all of like the parent and sub children, it doesn't matter because all the processes are completely independent. So in this case, this is something unique to threads. Yeah.
So pthread exit will exit the thread.
Yeah.
All of the, if there are no other threads to run, like if that thread created another thread,
Yeah.
then it would wait for all those threads to finish first before that thread is finished.
Yeah.
Okay.
Yeah. Pthread just terminates a thread and will not terminate the process unless it was the last thread standing, in which case there's nothing else to run. Yeah.
Same question.
Same question? Okay.
So what's keeping track of like what threads exist and everything?
So question is, what is keeping track of what threads exist? And the answer to that is, it depends. So threads, we'll get into next lecture, can either be like user space or kernel space. So pthreads, in general, the kernel keeps track of that. So the kernel knows that you have a thread, but it doesn't actually, in this case, it doesn't actually matter. The library knows how many threads there are, so the library just figures it out. But yeah, we'll get into the thread implementation a bit later.
Just one more question. So
Yep.
if you didn't have the pthread exit, the reason why only in main prints is because there's like, what would be like the
Yeah.
concise way to say it?
Yeah, if I don't have pthread exit here, and I just have this, the concise way of saying it is, well, it creates a new thread. I don't know which one is going to execute next. It could be the situation where the main thread executes first, and it prints in main, and then it returns 0, which just exits the process, and then everything's gone.
Okay, but there is a chance that it would print, is what you're saying?
Yeah, there is a chance that I would see in run for the same reason, like when I ran it like 10 times, and then one time I saw in run first. So if I had that same ordering, I would see both messages. I would just always see in run first. Yeah, I either see in run then in main, or I see in main by itself. Yeah.
Can you just explain when you said main thread, are you saying like analogous to like main process?
So when I say main thread, yeah, this bothers me. Oops. So when I say main thread, so by default, whenever your process starts executing main, we assume that it's a thread that's executing it, because calling everything that's executing a thread is just way easier. So whenever your process starts, it by default starts with one thread called the main thread that starts executing main. So that's what I'm talking about here. So the main thread would start executing this code and then create a new thread. So now I'd have a main thread and then the thread I created that wants to execute run.
So it's like more accurate to say main thread than main process.
Yeah, generally no one says main process. They says main thread within a process. Yeah.
So pthread join waits for the child thread to finish an implementation.
So there's no real child threads. You just wait on a specific thread. Wait. So you have to wait on a specific thread. There's no concept of parent-child because they're all in the same address space. Yeah.
In this case,
Oh.
the main thread won't finish until the join thread finishes first, right? Like it waits for the. Sorry, like in this specific example, it creates the thread, and then it calls pthread join on thread.
Yeah.
So that the main thread won't finish before the thread finishes.
Yeah, so in this case, the main thread calls pthread join. So the main thread will not continue until that thread I called thread is finished. It terminates.
So this is like the equivalent of pthread exit, just when it's not detached.
Yeah. Well, kind of. Yeah, pretty much, because I'm waiting on another thread. So in the detach example, whenever I exited, I actually I actually terminated the main thread. In this, I just have the main thread wait for the other one. Yeah.
So in the detached error example, with pthread exit, the return 0 doesn't get executed, just the pthread exit that like exits from the thread and the
Yeah.
thread, right?
Yeah, so if I have pthread exit, this never happens. Like, this is dead code because the main thread's now gone. So
And in what case would that not happen? Like, just explain like if you have pthread exit,
yeah.
is it possible that the main thread will not exit?
No, so in this case, it's not possible that the main thread doesn't exit because remember, this thread returning from here is the same as it calling pthread exit. So I could make it the case of like, if you get super unlucky, because there's nothing stopping this from just calling exit. So if I do something silly like this thread can just end the process and then everything's gone. So if you have another thread that just calls exit, yeah, then that's your fault. Yeah.
Just to clarify on what he said, so if we didn't create any threads and we called pthread exit, that's equivalent to calling exit.
If you, in here?
Yeah, like let's say we do int main pthread exit. Is that the same as exiting without creating any threads?
Oh, like just what, like that?
Yeah.
Yeah, so there's a main thread. So here it would just exit the main thread and now there's no other threads. So it just exits the process. So it would do the same thing just with more steps.
So there's nothing stopping you from like creating threads within the run, and
Yep.
maybe even forking within the run.
Yeah, there's nothing stopping you from creating threads in the run. There's nothing stopping you from forking in the run.
And then in your fork, you create more threads, but now they're in different address spaces, right?
Yeah, you can fork and create more threads or do it. That's when things get fun. So you might think that is a recipe for disaster. It's actually not too bad. So there are rules behind it. Yep.
So can you just describe what is the attribute unused parameter in the run function?
So the attribute unused.
In the function definition, there's a, like if you scroll up to, line 4, what is
Oh,
this?
yeah. So the question is, what the hell is this thing? So this is essentially what the hell do they call it? A compiler attribute. So this is basically me getting rid of a compiler warning. So you know the warning like unused variable? This is me acknowledging to the compiler, I know it's unused, don't warn me about it. So this is just a compiler thing just so I don't see a warning message. And that's just because I hate warning messages. I don't want to see them. So this is squelch the warning message because yeah, I know it's unused. It's fine. Yeah, whatever. That's a good habit to get into too. Max warning levels and make sure your code compiles without warnings. It's a good tip. I don't think I did that for like years. Yeah, so here is that example. So whenever we throw pthread exit at the end, if we detach the thread, well, we have to exit from the main thread, do a pthread exit from the main thread instead of just returning 0, because we need the process to still exist, and this will always print the 2 lines, and we don't know in what order they're going to be printed in. So that was our fix. All right, so here's attributes for that third parameter. Also, you can like use them to query information about the thread. So for instance, if you wanted to get the stack size, well, you can use attributes to get the default stack size. So here, you just have an example that prints the stack size. Whenever you run this on Unix or on Linux, I'll save running it due to time, but the stack size is by default 8 megabytes. So if you go over 8 megabytes, right, we talked about the guard page, there'd be a guard page after that, and then you get Stack Overflow and all that fun stuff. So in here, you could also set the thread state to joinable if you wanted to be super explicit about it. So you just take this attribute structure and you can use set detached straight and look it up, and then you can create it joinable. You can also have it so that you create threads that are detached. So you could change that to pthread create detach, and you don't have to do the detach one. But typically, that's why they give you the nice little helper function. So let's see in this. So whenever we had multiple forks, we will probably run out of time. So when we had multiple forks, we had something like this. So we could have a for loop that creates 4 new processes. In that, well, I could call a new process function, and in the new process, all it would do is call fork, and then if it is the parent, it would just return, and then the new process would execute the useful work. So here is all the useful work that the child process is supposed to be doing, and then it would eventually exit and terminate, and everything could run at the same time. No, multiple fork. Oh, wait, it's called. So in this, I create 4 processes, and they all just essentially just count from 1 to 0 all the way up to 9. So if I did that same thing using threads, oh, I'm running out of time. If I'm doing that same thing using threads, it looks like this. So the main part looks essentially exactly the same, have a for loop, and I create a new thread each time. Instead of here, I would do a pthread exit. Then in the new thread, it looks a bit different because I want to pass an argument for it. So whenever I'm doing multiple forks, well, I have a counter, and whenever I fork, both processes are exactly a clone at the time of the fork. So I don't have to like make a new copy of the variable or whatever. I just let virtual memory figure it out. That loop counter will be different for each process because I fork it at a different time. With threads, they're in the same address space, so I can't do that. So if I want to pass things to a thread, I have to use probably malloc, I have to use pointers and all that fun stuff. So here I declare an int pointer, and I malloc the size of an int, and I essentially write the ID to that memory location. Then I create a new thread, give it a run, and then I pass that pointer to it. So if I pass that pointer to it, well, now I can take that void pointer, cast it to int star, because I know it is an int pointer, and then I can dereference it to get the ID out of it. Then after that, I have to free it because I'm done with it. It's the same case. I malloc in the main thread, pass it to the thread, and now it essentially is the only one that owns it, so it needs to free it. Then I would do the same thing, count for that, and if I run this, it should essentially do the exact same thing. does the exact same thing, except the order's a bit different. And yay. All right, so we can continue over this because we're out of time. So just remember, bone for you, we're all in this together.